Greetings. A very common problem for engineering students is to learn the second law of thermodynamics. The problem comes since we take a different approach to the second law of thermodynamics than what we did for mass conservation and the energy equation. So the student finds a gap and loses the path. Let me explain for you further what I mean. Look, this is the mass conservation equation. What it is telling us is this, that the change of mass inside the control volume is a function of the mass that enters and the mass that exits. Very simple. Nothing else affects that mass. The white here to the right is very important. Since there is nothing, it shows that there is nothing else that can change mass. The first law of thermodynamics takes a very similar pattern. It gives you that the energy is another property. The energy change inside the control volume is a function of the energy that enters with the mass that enters, a similar term than this one, the energy that exits with the mass that exits, a similar term than this one. So we have three similar terms in these two equations. And instead of the white here, there are two other terms that can affect energy, namely heat transfer and work. Now, by the time the student comes to learn these things, and almost all um, major thermodynamics textbooks that I know of um, repeat almost a similar pattern these days. So the student comes to learn these two equations, and with that, he learns how to calculate or read properties, or how to calculate work, what is work and what is heat transfer. So the student comes to get very familiar with these two equations. Now, once we are finished with the first law of thermodynamics, instead of introducing a similar pattern for the second law of thermodynamics, we go to a very different path. The path we take is that usually we usually start with telling him what is a heat reservoir. Heat reservoir. What is a heat reservoir? Then what is a heat engine? What is a refrigeration cycle? And then we tell him two very unusual statements, which are Kelvin Planck and Clausius statements. Kelvin Planck and Clausius, which basically are negative statements, and they state negative things. It is impossible. So after that, we prove that if one is wrong, the other one is wrong, and if the other one is wrong, this is wrong. So we go to a pattern of very different from where we ended up with the first law. Then we continue with Carnot, and we uh, present two Carnot statements and then prove that the two Carnot statements are equivalent. And then we prove that if they are equivalent, any of these things, they are equivalent with any of these two statements. And then we go to Clausius inequality, which basically is an inequality and very unusual for a student to handle. Many students are not used to handle inequalities, and then gradually we come to the equation of the second law for a process. Second law equation for system and not a control volume, and for a process and for process. So this path is a very, very long, tedious path. Every step that I have mentioned is unknown to the student and has to learn new concepts, new ideas, which are not really what he should handle later on. I mean, a heat reservoir is something which is okay, we have examples for it, but after this chapter, we won't use it that much. Kelvin Planck and Clausius statements are something that we don't often use in any engineering problem. Clausius inequality is the same. And so this provides a gap into our equations. You see, we have finished this equation of the first law. We have spent about a month at least to handle those difficulties. The student has lost touch with all this pattern, and then we gradually reach this one, and we try hard to bring the student to a pattern which is similar to what he already knew after the first law was introduced. So, what I'm going to do is to start a new way of introducing the second law. And this method I have used for many years in my classes. The students are happy, they understand it. It is tested, and I hope this will help you as well to learn the difficulties of the second law and bypass what is a treacherous path, I assume, um, to go through Kelvin Planck, Clausius, and all those statements. It's not that we ignore them and we get rid of them. No. What I would do is to start from this place for the second law for a control volume. In fact, I would start from this equation and then would gradually go back to say to second law for system, to Carnot statements, Kelvin-Planck statements, and refrigeration cycle, heat engine, heat reservoir, and then define the Carnot cycle, Carnot efficiency, and show, in fact, that if we are able to start from Kelvin Planck and Clausius statements, then we are also able to start from this equation and conclude Kelvin Planck and Clausius state. Well, let's assume we are in a position that we have learned the mass conservation equation. We know that this is the change in mass inside the control volume is a function of that the mass that enters and the mass that exits, and the change of energy inside the control volume is a function of that energy that enters with the mass, energy that exits with the mass, and two other terms, heat transfer and work. Now, I want to take a similar path to introduce to you entropy. Assume that there is a property entropy. There's a property, however fictitious, not true, but still. Assume that there is a property that if a process is possible, it increases. And if a process is impossible, it drops. What do I mean by this? So, I would write it down. But assume that there is a property, however unreal, okay, that increases in possible processes. What do I mean? I mean, assume that there's a property. This is the axis of that property. We name it entropy. Entropy. We name it entropy. And what we do, we say that if that property has a value, okay, just like energy, just like mass, just like a specific volume, just like any other property, assume that this property has a value in a state, in a certain state. Now, if a process happens to that system, okay, if a process, and we assume that if that process is possible, then this property increases. So if at state 1, this is S1, then for a possible process at state 2, this property increases. So this would entail a possible process. A possible process is a process where the property entropy increases. We are defining entropy to have this um, behavior. Okay, we are. So if I have this pen, okay, assume if I drop this pen, is a possible it will go down. This is a possible process. So entropy should increase. But if it goes up, entropy should drop because it is an impossible process. So S3 is less than, here S2 was larger than S1, And here S3 is smaller than S1. So this would entail an impossible process. An impossible process is a process where the entropy is reduced, decreases. And the possible process is a process where entropy increases. Note that we are not claiming that entropy would only increase or decrease with the possibility of a process. No, that's not the case. Other things could change entropy as well. We shall discuss it later on. But we define entropy as a property, however fictitious, however unreal, that would increase if a process is possible. And we call that, we say that S2 minus S1 equals Sgen, which is the generated entropy during that process, because the process is possible. So for all real processes, for all real processes, for all possible processes, entropy should increase and Sgen should be positive. So for all real processes, for all possible processes, Sgen should be positive. Okay, and for all impossible processes, Sgen should be negative. That is where we start. Instead of starting second law of thermodynamics with Kelvin Planck or Clausius statements, we start from here. Okay, we start from here. So there is a property which increases if a process is possible. And where entropy does not change, that means that the process is on the borderline between possible and impossible. So Sgen equals 0 is the borderline, is the borderline between possible and impossible processes. Sgen equals 0 is the borderline. So this was the axis that I drew for S. But if I draw another axis for Sgen, generated entropy, then here, when Sgen is possible, this means all possible processes. If it is negative, it is all impossible process, and 0 is the borderline between possible and impossible processes. Okay, this is how we define this is how we define entropy. I insist that entropy does not exclusively change with the possibility or impossibility of a process. No, it could. There are other things that could change it, but This is a property where S could change and Sgen is positive for possible process. So we defined entropy as a property that should increase if a process is possible. Let's write an equation for it. If entropy is a property just like mass or energy, not like them, similar. What we could write is that the change of entropy inside the control volume is a function of the entropy during a process. Okay, the change of entropy during a process inside the control volume is a function of the entropy that enters with the mass that enters minus the entropy that exits with the mass that exits plus the entropy that is generated because the process is possible. In fact, we could write this simply for any property. At least this is the minimum requirement for every property. In this shape, entropy has no dimensions. In fact, it can have any dimension and has no relation to whatever we have learned up to now. It has no relation to all the terms we knew that could happen. It has no relation with heat transfer, no relation with work in this shape. Okay, in this shape, it is not a property that we can calculate or put any value to it or enter it into our calculations. First law, mass conservation law, that we already know it. So what we add to this equation is one term which um, I introduced to you, and that would relate entropy to everything. And the term that we introduced is Q dot divided by TB, which is heat transfer divided by the temperature of the boundary where that heat transfer occurs. So why we are doing this is irrelevant at the moment, because this is how the second law of thermodynamics is. You see, uh, when you go driving, when you go to learn driving, they tell you this is accelerator, this is brake, this is the steering wheel, and this is the gear. Why there is an accelerator and there is a brake where you could just do all this with a joystick? That's not the point. This is how it is, and we learn to drive with it. We learn to use it and drive with it. Later on, you might ask why it is so, and that's a valid question. But to start with driving, no one takes you to the details of how a car operates or why the car is like what it is today. This is the same story. Second law of thermodynamics is like this. And first, we should learn how it looks like. Then we should learn how to use it. And then, if it was necessary, we should learn where it came from, who did develop it like this, and what were the incentives to make it appear like this. But it is a very important point to learn how we how we use this equation, and what does this term q over the boundary term do, and why does it make this equation a very useful equation? Because it is using heat transfer and the temperature of the boundary that heat transfer occurs as a means to show what is possible and what is impossible. And that is interesting. It is using a very basic natural concept that if you have two bodies, one hot and one is cold, the possible process is the heat transfer between the hot body and the cold body. This equation, this term, is introducing the possibility of every process in nature and in industry to the very, very basic fact that we all know that the possible heat transfer between two reservoirs, two materials, between two control volumes, between two surfaces, is from the hot to the cold body. And I show now how this term would just do that duty. Well, let's assume that there is a wall. Let's assume there is a wall. At the left side, the temperature is T equals 400 kelvins. And on the right side, T equals 300 kelvins. Okay, 400 kelvins and 300 kelvins. And there is a heat transfer of 10 kilowatts across that wall. Well, the problem is steady and there is no work, there is no mass that enters or exits. It's very simple. What we do is we choose a boundary. This is our system. And for that boundary, we know that M2 equals M1 from the M2 equals M1 from mass conservation law. And since there is no change, there is no mass entering or exit, there is no work. Therefore, Q in would equal Q out, and that would equal 10 kilowatts. So as far as the first law and the mass conservation law are concerned, the things are very simple. Now, let's write the second law for this wall, how it would look like. There is no change in property because any property, including entropy, because it is steady state, no mass entering or no mass leaving. Therefore, we have this term 0 equals S dot gen plus Q dot, which is 10 kilowatts, divided by the boundary, which is 400 kelvins, which is 400 kelvins, and plus minus 10 because heat is going out from the other side, divided by 300 kelvin. Okay, this term 10 divided by 400 is 0.025, and this term is 0.033, and therefore S dot gen would equal, bring it to the other side, and it would be 0.033 minus 0.025, and that equals 0.008. What's the dimensions? Kilowatts per kelvins, and that is the dimension. S dot gen is positive, and therefore the problem is possible. Now, if it were that heat transfer could go from right to left, if it were to be this one, then um, this term would be positive, this term would be negative, and the answer would be minus 0.008, which is impossible. And this one was possible. So what we see is that this one is possible. So we see that the second law is using the very basic fact that heat transfer is always from a warmer body to a colder body to decide what is possible and what is impossible. Now, what we should do is to return to this axis I draw and talk a little bit more about this place. Okay, and the process where S2 equals S1 and S3 equals S1. The process that is, in fact, the borderline between possible and impossible, and tell you what makes a process possible. In fact, we have to discuss what makes a process possible. And I shall continue with that subject in the next video. Thanks. Cheers.